As science worked to understand the properties of electromagnetic radiation, which I talked about some of the basics in a previous video for this chapter, there began to have an accumulation of evidence that atoms themselves, when they were excited, and another way to think of it, when they were at high temperatures or had energy put into them, that they would also emit light. So how you might put energy into atoms, one would be to put electrical current through it, or another way might be to place something in a fire, and that gives a high temperature and this energy to atoms. You actually are familiar with this phenomena in the form of neon lights. So think about a neon sign, and when the electrical current is off, no light is emitted. But when you turn the electricity on, the electrical current goes through the gas, and it turns the light on. And what we're seeing is light that's emitted from the atoms that have had the energy placed through it. So if you take that light and you pass it through a prism, and a prism would be like a crystal. So I want you to think, if you have a crystal and you shine and you get it in the right angle and sunlight shines through the crystal, then on the ground or on the wall you can see a rainbow, all of the colors of the visible spectrum that are separated from that white sunlight. And that's how prisms work. As the different energy wavelengths of the light go through the prism, they refract at different angles, and it causes a separation. So scientists would place the light from something like neon gas, but it could be any of the elements, through a prism like a crystal. And when they did, they saw a separation of the colors of the lights that were coming out of that one your main source. And that's called a line spectrum. And you can see in the picture here on the slide, there's a hydrogen emission spectrum right here. This is a line spectrum. So how this was collected is you take a tube of hydrogen gas, you put electricity through it, and it glows like a neon light. Then you place that light through a small slit. You put a little slit in front of it, and that goes through a prism, and you get these different colors. So you see it separates. We have a red line, a teal line here, a red line here, a teal, a blue, and then these kind of violet lines down here. And then notice that in between the lines there's dark space. Well, in the early 1900s, Niels Bohr, who was a Danish physicist, was studying the line spectrum of hydrogen, and used it to help understand the atomic structure of the atom. So what this led him, by studying the structure, again, see how there's colors? So you have the red line, the teal, this teal line, the blue, and then the violet lines with space in between. That led him to this model that looks like a target, where we'd have the nucleus in the middle, and then what he thought where the electrons were orbiting around the nucleus in with very specific energies. So the electrons would be on these paths. And Niels Bohr did think that they would be orbiting. So he studied hydrogen, and he created, he has actually equations for energy that he could relate the energy of the lines of the spectrum, because remember, different colors have different energy. He could relate the energy from the lines of the spectrum to the model of his atom. It was a mathematical model. Well, let's look how might you get these lines? How would this work? So if you look over on this figure on the side, this is what would happen when the electrons are in the lowest energy that they have, and this is how they would just be found before you put electricity into it. We call that the ground state. And if you put it, I'll draw my little electron as an arrow. Here's one down here. Now if I put electricity through it, so I put energy in, what it does is it excites that electron and it jumps up to a level. So now it's up here, but electrons don't really like to be excited. And so what it does then is it relaxes back down to the ground state. And then when it does, it emits that energy. And if the energy is in the form of, it has a wavelength in the visible range, then we see the light. And that's where the colors from the spectrum are coming. Here they have another blue one that's an example. So you could have another electron, and it absorbs more energy, so it jumps up to this excited state. See, and it's going to go back down, and when it does, it emits energy. And we see that, if it's in the visible range, as one of those lines. Well, if you notice again, I'll look at Bohr's model. Do you see that might be the first level? That could be your ground state. Here might be the second level. So imagine, here's the electron. You put energy in, it jumps up to, it jumps up to the next level when we put energy in, and then it goes down and we see light. And so we know that we can calculate the light based on the energy, based on the wavelength. And so now we know the energy between these two here. Now, the contribution of Bohr, what his theory that he thought is that the energy, is quantized. Now this is a very important idea. The quantization of energy is a very important idea in understanding our model of the electrons. And what it means is, you see the word quantity, the energy is quantized. That means that the energy that the electron can have will have very specific energy values. Okay, I imagine, and I didn't make up this analogy, that when quantized is like walking upstairs, right? To walk up a stair, if here's my foot, I have to place my foot on a step. And if I raised my foot above the step, it wouldn't stop here, it would fall back down because there's only certain places. And I could even skip a step, but to go up the stairs, I would have to put my foot on another step. That's quantized. There's only specific places that I can put my foot. And the energy of the electron, if you look at his model, is quantized. Here you could have this level, you could have this level, you could have this level, but the energy cannot be in between the levels. Right? It can't be, we don't see light or energy coming out that is in between the levels. We only see certain light. Remember that spectra had black, then the black just represents where no light is coming out, had black spaces between the colored lines, telling us that there's only certain energies that the electron is dropping out from. The opposite of quantized would be continuous. And if something was continuous, it would be like white light, like we see in the rainbow, where it just moves from color to color to color to color to color. There's no separation in that. A continuous could be like a ramp. So I could put my foot anywhere on a ramp. Little steps. I could put big steps, anywhere. There's not a certain place I have to land on a ramp, and that's continuous. And if the energy of the electron around the nucleus was continuous, we wouldn't have those big black spaces that we see in the line spectra, which indicate that there's no light or energy coming out from those levels. So Bohr's atom, once he studied hydrogen, and the spectrum I showed you at the beginning was from hydrogen. So he studied hydrogen, which only has one electron. And the mathematical model he developed worked really wonderfully for hydrogen. It predicted the things that we see experimentally with hydrogen, and it was great. When they started to try to apply this model to other atoms that had more electrons, they found that it did not work as well. So the model is going to have to be changed. Now, it's still helpful. What he really contributed, and he did win a Nobel Prize for his contributions. Two big ideas continue with us. One is that he suggested that the energy levels are quantized for the electron. And in the next model we look at, we're also going to consider and continue that idea of the quantization of energy. And the second thing he contributed was demonstrating that the spectral lines, the colored lines we see in the spectrum, result from the radiation of the energy that's released when the electron moves from one level to the other. So he was able to relate the spectrum to how the electrons are behaving inside the atom. So Bohr's model is a helpful tool for us to begin to understand the structure of the atom, but it does not help us predict everything we need to predict, including our bonding. As things went on, we'll see that some new ideas were mixed, including the idea of using wave properties as a part of our model for understanding the electron. So I'll do a second video for that, or another video for that.